Good afternoon, everybody. My name is Sean Patchett, and today I'm going to be your instructor. Today's lesson is going to be on airfoils. I'm going to go ahead and show you a little clip of an airfoil in a smoke tunnel. It shows a pretty good demonstration of it, so here you go. And we're back. I really like that video a lot. It showed a pretty good demonstration of as that blade, the pitch was increased in that blade, how the separation of air begins at the trailing edge and works its way up the upper camber of that airfoil and basically until stall is reached. So I thought that was a pretty good little demonstration there, and hopefully I got your attention. So we'll start off with basically the definition of an airfoil. It's basically an airfoil is any surface, such as a rotor blade of a helicopter or an airplane wing, which provides aerodynamic force when it interacts with a moving stream of air. Today we're mainly going to be talking about rotor blades, R22 rotor blades specifically, and a little bit of just general helicopter rotor blade design and stuff. So with rotor blades, there's two type designs. So you basically have symmetrical and asymmetrical. Airfoils. So we're backtrack a little here. We're going to talk about type and the components of airfoils. If I have time, I might get into aerodynamics just a little bit, depending on how long this takes. So first we're going to talk about symmetrical airfoils. Symmetrical. All right. So basically with the symmetrical airfoil, you have the upper camber and the lower camber, basically bisecting that airfoil in two parts, the upper camber and the lower camber. With a symmetrical airfoil, the distance of each upper and lower camber is the exact same distance. Here we have our leading edge. Here's our trailing edge. And if you draw a line from your trailing edge directly to your leading edge, that's going to be our chord line. Okay. As you all know, the R22 probably has, or you probably know that the R22 has symmetrical airfoils on it. What makes some characteristics about symmetrical airfoils is that they're very stable blades. The center of pressure in them stays relatively unchanged throughout its flight path. What the center of pressure is basically it's an imaginary point along the chord line here that basically where all the aerodynamic forces that are acting upon the airfoil, all the resultant of all these forces is considered to be concentrated. So you can just kind of imagine a little point here, and it basically doesn't move. And I'll talk about the center of pressure a little bit more with asymmetrical airfoils, because it does tend to move a lot more in that design. So we'll get into that a little bit later. But basically, since that center pressure doesn't move with this, like I said, it makes it very stable. Blade twisting and flight control loads are minimized a lot with this characteristic. So that basically equals stability. And symmetrical airfoils are, in general, they're just easier to make, they're cheaper to make, there's less internal stress because of their stability, but they are, they're not as efficient in producing lift as a symmetrical airfoil is, so it's one of their downfalls. Now we're going to go ahead and talk about asymmetrical airfoils here. Let's see if I can draw one here. That's kind of good here. It's a little exaggerated, but we'll do that. Okay. So an asymmetric airfoil, as you can see, the upper camber and the lower camber have unequal distances. Typically these airfoils are less stable than symmetrical airfoils, as I talked about earlier, but as you can see here, one thing they do to kind of counteract this is the trailing edge is bent a little bit. They bend it a little bit, and which is also referred to as reflexing, and this tends to give it similar characteristics to a symmetrical airfoil, so it stabilizes it a little bit more. But like I said earlier, the center of pressure with an asymmetrical blade does tend to move forward and aft throughout its cycle of rotation. Basically, when the center of pressure moves, it kind of corresponds with changes in angle of attack. And basically, when the angle of attack increases, that center of pressure is going to move up or forward on the chord line, and vice versa. As the angle of attack is decreased, it's going to move backwards. Another thing they refer to is the pivot point. I'm just going to go ahead and kind of draw a circle here. You can kind of imagine that as being like the rotor hub of the rotor system, and that's kind of the pivot, or the axis of rotation or the axis that the blade pivots on. When the center of pressure moves outside or in front of this pivot point, the entire rotor disc, it decreases the pitch of the rotor disc, and as it moves to the rear or behind the pivot point, it increases the pitch of the entire rotor disc. And so since the angle of attack is constantly changing due to the dissymmetry of lift, where it's always flapping down on the retreating side and flapping up on the advancing side, that center of pressure with an asymmetrical blade is constantly moving. So basically what that corresponds to is the flapping, the feathering, and the lead and lag happens to a greater degree throughout the cycle of rotation, so it kind of creates a pendular or a wobble, more of a wobble in the rotor disc, and thus giving it its kind of unstable characteristics as a rotor blade. Some things about asymmetrical blades is that they are harder to make, they're more expensive to make, they're more, like I said, more expensive, there's more internal stress, cause the blade twists and stuff occurs, and they sort of beat themselves up a little bit more than a symmetrical blade does, but they do produce more lift. They're more effective in producing lift. So that's what you got with the two types. So now we've covered types. Now we're going to go into the components of an airfoil. So we are going to be talking about the R22 blade here, which is a symmetrical airfoil. So this is the R22 blade. Go ahead and draw the components of it here. Okay. So up front, at the front of the blade, we're going to have what is called the spar. It's a stainless steel spar. The spar runs about a third, I believe about a third of the length of the blade from the tip towards the rotor hub. It's basically just because the tip of the blade moves at a much higher speed than the inside of the blade. Thus, it encounters more friction. Then we have two stainless steel skins on the outside of the blade here. And this right here is going to be our bond line. So here's our spar. We have skin here, and this is our bond line. And then inside is a bunch of aluminum honeycomb. And I have a picture here of an R22 blade that has actually been delaminated. But it also is a good diagram of all the components. So here you have the spar, you have the cap, the tip cap, you have the honeycomb, that is the aluminum honeycomb in there, and here's the skin. There's also going to be one on the other side, of course. And this right here is our bond line. Basically, over the entire blade here, once it's adhesed, once the skins are glued to the spar here, the whole blade is coated with really heavy-duty paint. And we all know with our blade airworthiness directive that we do on all of our pre and post flights, or mainly our pre-flights, you got to check and make sure that bond line right here isn't exposed. Because as you can see, there's a little gap. Once it's been exposed, there's a gap in there, and once that air starts getting in there and it creates a lot of drag and it starts getting under that skin, it's just going to peel it. It's going to debond that, delaminate that, and peel it right back like a tin can. Another thing to look for is this cap here you can get water in there, and essentially you can get some corrosion. So that's another good thing to look for on your pre-flight, is look around the cap and look for any corrosion that might be occurring around the blade here. And that bond line is exposed, then you just, obviously we have to squawk it, and the helicopter blades need to be recoated. And typically, if you notice it on one, it's going to be on the other blade as well. So our blades are 12.5 feet long from the rotor hub to the tip, and the cord from leading edge to trailing edge is 7.2 inches. 7.2 inches. They have a 2,200 hour service life, and one thing I learned in the safety course is that the blades are balanced as a pair, so both must be replaced every time, even if only one needs to be replaced. It's just too hard to try and balance a new blade with the existing blade that's on there. So that's basically all we're going to cover today about airfoils. I'm not going to get into aerodynamics because I'm running out of time here. So in review, I would like you to explain the differences between symmetrical versus asymmetrical blades, and draw an R22 rotor blade and include and label its components. And I think that's going to wrap up our lesson. Thank you.